Good afternoon, everyone. My name is Waravet Cholasins. My nickname is Joe. I'm the Executive Director of AIT Extensions at the AIT in Thailand, in Bangkok. So I have to say maybe good morning, good afternoon, and maybe some of you are already good evening. So today is one of the online sessions that AIT Extensions organize almost every 2 weeks in order to spread the information about the interesting topics and also interesting emerging issues in our region. And today is also one of the very special sessions that we are having in the recent months that we are try to also work with different partners from different countries. And at this point of time, we also, bring in our collaborators and friends from other countries to join us to sponsor the online event with AIT and with AIT Extension. So I want to say that, this event will not be able to happen if we don't have a good partner like TQR insurance company in Thailand, and also we have a collaboration with the Nepal Insurer Associations and also Professional Advanced Bangladesh, which is one of the group of the companies in the insurance in Bangladesh, and also we have others, friends and partners that helping this event to happen today. So before we go into the program, I would like to invite my friends who are now sitting in Kathmandu, in the office in Kathmandu, from the Nepal Insurer Association, Mr. Shanki Chetri, to welcome the audience to this event. Shanki, please.
Namaste. I'm Shanki Chetri, President of Nepal Insurance Association and the CEO of Shaliko Insurance Company. So today we are going to have one webinar meeting regarding the earthquake. As you know that Nepal is also very vulnerable country in respect of the earthquake zone. We have already faced the pain and gain in 2015. So recently I met Mr. Bowit at Bangladesh, then in Bangkok, then one seminar in Nepal, it was held in last month. So we thought why not to exchange our experience about the insurance matter related with earthquake. So the topic is like earthquake, this Turkey earthquake. Recently we have hit by the earthquake. So Mr. Professor Pangwing is going to exchange his experience about the Turkey matter. So the thing is that what can we do from the insurance side to just make the financial losses from the earthquake this time? Because we can't avoid that the natural calamities or anything happen in the world. We can't avoid. But the thing is that we can just minimize the losses, financial losses from this sector. So nowadays, because of the pandemic and the COVID is taking so many risks and climate changes, these are the things which are affected all the human beings globally. So I think today we are going to take the knowledge from Mr. Professor Panin, and I would like to welcome all of the participants from the Nepal, Bangladesh, and other countries on behalf of the Nepal Insurance Association. And I hope we will do this such kind of program in future also. Not only webinar, we will go for the this type of seminar with collaboration of the AIT, because AIT is a very famous university in the Asian Insurance Institute. When I visit, I came to know they are doing so many research and development work over there. So it's good for our employee or our staff to motivate them and make the encourage to contribute their participation in this field. So thank you, Mr. Bobrit, who has accepted my request for this webinar. And welcome you all. Thank you very much.
Thank you, Mr. Shanki. Thank you, very kind of you that we can also start together. This, networking is very important. We started this webinar because we went together into Kathmandu and also into Dhaka city, to have the conference related to the climate risk. insurance. And then we found that one of the hot issues, one of the hot topics among the insurance professionals and also construction professional, engineer professionals is the disaster, which is, caused by the, earthquake. So that's why we came up with the idea, let's have the expert who have the highly knowledgeable and also practical experience in the earthquake engineering to make a presentation to talk to you today. So our session will be about 1 hour or so. So you can enjoy listening to professors. And also after that, if anybody have any questions or any, comments or suggestion, we will be open the floor to everyone. So let me just have a quick introduction of the webinar and also the speaker today. Our webinar today is on the topics of the earthquake engineering, taking the lesson learned from the HIPS in Turkey. So a few months ago, we had that problem in Turkey, and so we can explore from the presentation from Professor Penning Wanitchai today. Professor Penning has been working in this seismic engineering for many, many years. He also joined the mission into the country where earthquake happening, and also looking at the, how the impact of the earthquake, affect to the buildings and also the destruction on the site. From that perspective only, that we can find, we can explore the issues from the engineering perspective, from the risk perspective, and also from the social impact perspective from the earthquake engineering aspect. So without further delay, I would like to now introduce Professor Penning Wanitchai, and also request Professor Penning to start his presentations, his information to you. Professor Penning, please.
Okay, can I start now?
Please.
Good afternoon, everyone. I will just take a few seconds to share the slide. Okay. What I'm going to give a talk today is about earthquake risk and how we are going to prepare ourselves for the future earthquake. Initially, I thought that the audience will mainly come from Nepal. So I use a lot of photos from Nepal. But I also added some photo about Bangladesh as well. So let me start the story. I have about nearly 80 slides, so I try to finish them in 1 hour, I hope. Okay. Let me first give you this basic background about earthquake. This first slide shows you the distribution of earthquakes around the world. The red dots, each one shows the epicenter of each earthquake event. Well, you can see from the slide that earthquakes are actually concentrated in some area, some zone. They are not uniformly distributed. They are highly concentrated in some zone, some area. Some countries like Japan, Philippines, you cannot even see the country. It's all covered by earthquakes. But some countries like Australia, there are just a few earthquake events. Why earthquakes are concentrated in this particular area? I think what you need to know is that most 95 or more of these earthquakes are actually produced by tectonic process. The Earth's outer shell is actually is not in one piece. It actually consists of many pieces we call tectonic plates. Some plates are quite large, some plates are small. And they are moving in a different direction as shown in this slide. When they are moving in different direction, it will create the conflict of the movement, mainly at the boundary between them. It will create a large interacting force. It will produce a deformation in the rock, in the plate materials. It will create a stress in the rock. And this one, the force, the stress, the deformation in in the rock, in the tectonic plate will increase every day until one day it's too high. Then the rock will break or may slip and release the energy and it's turned into earthquake. So by this mechanism, most earthquake will happen near to the or at the boundary or near to the boundary. So if you look at this slide and we go back to the previous slide, you can see that most of the earthquake happen at the boundary or near to the boundary. Okay. Now we come back to the tectonic plate map again. Now let's zoom up to some particular area. For example, in Thailand, the picture on the left show the tectonic map. You can see Thailand, Malaysia, Myanmar, Laos, China. They are all located in one plate. And India is on the other plate. And the plate of India is moving toward our plate at the speed of around 65 millimeters per year. The rate of movement is very slow. If you watch them move, you cannot see that they are moving. But they are moving. And the point is, the boundary between them, you can see that part of that is in the Andaman Sea, under Andaman Sea. And on the right-hand side, you can see the distribution of earthquakes. So they are actually happening or concentrate along this boundary between these two plates. The boundary between these two plates is also continued to the north. You can see Himalaya mountain range. Actually, Himalaya mountains are also created by tectonic action. And recently in Nepal, you have a large earthquake happened. They call Golkha earthquake in 2015. This is also happening at the boundary between these two plates. Now let's move to another area. This is Turkey. Some people call Türkiye, but let me call this Turkey. So this country is located in a very complex tectonic condition. We have a Eurasian plate in the north, Anatolian plate here, and we have Arabian plate in the south. And these plates are moving in a different direction. The boundary between the two plates in a Eurasian and Anatolian plate is, we have an active fault called North Anatolian Fault. That fault actually shows the boundary between these two big plates. And the movement between them, they have a relative movement between them at a rate of around 18 millimeters per year. So the higher rate, then the more earthquake activity. And the boundary between Anatolian plate and Arabian plate is, you have an East Anatolian fault, and we have the rate of movement around 8 millimeters per year. So these are two very large active faults in this zone. You can expect that there will be many earthquakes happening basically close to this fault or on this fault. Okay, let me show you the next picture. This shows you the distribution of earthquake. You can see many circles. The orange color show large earthquakes. The yellow color is also moderate to large earthquake. So you can see many earthquakes happening in Turkey over the past 100 years. Okay, so based on this information, and the expert in Turkey create what they call seismic hazard map. This one is seismic hazard map. It shows you the maximum ground shaking intensity that will happen by earthquakes with very long return period. We call this 500-year earthquake. this type of earthquake you will see only once in 500 years. Okay. The color show the level of ground shaking intensity. If it's green, it's light, low intensity. Yellow is become higher, red is high. And if it's dark red or violet color, it's very high. So you can see there in the north, you have the zone along North Anatolian plate, very high. And in the south, you have East Anatolian plate. So these are the zones that they already expect large ground shaking intensity. They already expect damaging earthquake to happen along this zone. And then this year, February 2023, they have a big earthquake, Turkey, Syria earthquake. The location is along a portion of East Anatolian Fault. If you look at this and you go back to the previous slide, it is actually this area, the area that they already expect this to happen. Okay. Well, in this slide, you can see the color, many different color, but the red zone show very strong ground shaking. And many triangular dot in this map is show where they have seismic instruments that they record the ground motion. So by this earthquake, Turkey then was able to collect a lot of information about ground motion. But by this earthquake, 160,000 buildings destroyed and more than 50,000 people killed by this event. So it's a magnitude 7.8, a very large earthquake. Now let's see the impact. Okay, you can see the impact is beyond our expectation. You can see the collapse of so many buildings in the area. The picture tells the story. I think if you follow the news, I think you may have heard about this one. Okay, a very high rate of destruction. Let me show you some video clip in the same area. Okay. A single large earthquake. Okay. Now, you know, this earthquake came without warning. We cannot give a warning, early warning for earthquake type disaster. We cannot predict when it will happen, where it will happen. We cannot predict. So the best strategy to handle this risk, to mitigate the risk, is to make sure that our buildings are strong enough to stand against earthquake. Okay? And to do that, we need to design and construct our building for earthquake resistance. But then there are many explanations why you can see a large number of damaged buildings, a large number of casualties. The first explanation is that a large number of buildings were built before modern earthquake-resistant building design standards were introduced in Turkey. Okay, that's one of the explanations we have. And I have heard, okay, they have recently introduced modern standard, but before having this modern earthquake-resistant design standard, a large number of buildings have been built already. Okay, so they are more vulnerable than new buildings. The second explanation is that after we have a new standard, still many new buildings were designed and constructed without following the required standard. I was told, I see from the news that it is possible to buy building permit if you pay some amount of money to authority. That's what we heard. Okay, so there's many ways to avoid following the standard. The enforcement system was not so strong. Okay, so if you have regulations, you have standard, but nobody follow, then it will not be effective in provide the protection to your buildings. And the third one, I think, is also quite important. The intensity of ground shaking was higher. I can say much higher than the level expected in the standard. So in the standard, we assume some level of ground shaking, the maximum level of ground shaking. But then for this case, the ground shaking turned out to be stronger than what assumed in the standard. So let me show you some information. This is a bit technical, but I hope you will understand. The picture below, two pictures below, show the location of seismic instruments in the area affected by this earthquake. And they have record many ground motions. They have many ground acceleration record available from all these seismic instruments. And they use that to calculate what will be the maximum earthquake-induced force in the building. This is a lateral force produced by the earthquake in the building. It's shown you in the upper curve, upper figure. The vertical axis shows the level of maximum earthquake-induced force, but this force depends on many properties of the building. The key property is natural period of the building. So this one is plot the force against the natural period of the building. Let me give you some rough idea. 0.5 means 0.5 second natural period. It's related to building of about 5 stories. 1.0 second means building about 10 stories. And I think you can continue. Now, the standard, this is given by 3 curves, the red, the blue, the green for different soil conditions. All these standards show the level of earthquake-induced force in the building expected in the standard. It's based on the 500-year earthquake that may happen only once in 500 years. But the ground motion shown, we record, they can compute the level of earthquake-induced force, and many of them are much higher than the standard curve, the design standard curve. So you can see many of them exceed this level. So I show you another one. This is a 2,500-year earthquake with a very long return period. I think this one, the curve cover most of the case, but still there are some few cases that exceed 2,500-year return period earthquake. So we have 3 issues. We have old building that not following the standard, the new standard, and new building that also not following the standard. And also the standard is not based on the level that high enough to cover all this case. So if we are going to start working on earthquake mitigation of earthquake risk, the first step is to create the proper seismic hazard map. Okay, we have to convert the picture on the left, the distribution of earthquake or the location of active fault. We have to convert them into the seismic hazard map on the right-hand side. Okay, and this is show the level of 2,500-year earthquake intensity. Okay, so based on this, we can then know our target. We will know what is a maximum level of ground shaking that might occur in our country. And then you can prepare yourself for that level. So we have this kind of map long time back, and in Thailand we introduced the first step. After we having the proper seismic hazard map, the first step was to introduce the regulation. This shows you the first ministerial regulation for seismic design. It's required that buildings in the yellow color area, the northern, the western part, need to be designed for seismic resistance. Okay, that's the first step that we have to do. And after that around 10 years, then we introduce the guideline, or we call design standard. Okay, we need to have a regulation to make sure that people will follow, will design building for earthquake, and we need to have a standard for engineers, for architects, to make a proper design, proper construction of buildings and structure. So this is for the case of Thailand. We introduce the regulation first, and then we follow by the national standard to guide engineer to design building against earthquake. Now, after talking a lot about the need for earthquake resistant design, let me give you some rough idea. What are the things that engineers need to do to make sure that buildings can stand against earthquake? First, we need to make sure that it has some lateral strength. Lateral strength means ability to stand against lateral force. Okay, when earthquake shake your building, it's going to produce additional force, both vertical direction and also lateral direction. But your building already has some ability to carry some vertical load, because most buildings will design for gravity load, dead load, life load. So it has some strength, additional strength for additional vertical load. But most buildings normally are not designed for lateral effect. So we need to have some lateral strength. And in the code, in the standard, there will be several formula and detailed guides how to design this one. The second point is we need to make sure that the building will have some lateral deformability. Some people call this ductility. Okay, it means that under effect of earthquake, building will sway to the left, to the right in cyclic manner. It may create damage to some component, to columns, to beams. We have to make sure that after several cyclic response, the building will be able to stand and continue to carry the gravity load. Okay. We have to make sure that the damage will not concentrate in some particular zone, particular spot that are critical for load carrying capacity. If some columns are destroyed, then it cannot carry anymore the vertical load. The building will collapse. So in order to have good deformability and lateral strength, we normally have to try to avoid some configuration of building. I think if you can see the picture on the left top, soft story. This is one of the most vulnerable form of the building. The building with many walls on the upper story, but on the first story, you don't have any wall. You have only columns. So the structure is quite weak in the first story. Structure is quite soft in the first story. There are many other forms, like if you have the building that do not have the wall in the front, but you have the wall on the side and on the back, building is going to be twist when it's subject to earthquake. So we call this torsional irregularity. There are many other, irregular form as shown in this picture. These are just example, but I don't have the time to go through all this one. But as an engineer, we have to try to avoid design or construct a building like that. And this day, many modern construction, we build our house, our office, our buildings by using concrete material. Concrete is a strong material, but it's quite brittle. Okay, it cannot deform well. So we normally put steel bar inside the concrete. So it's become reinforced concrete structure. Concrete with steel reinforcement inside. Okay, but whether it will deform well or not depend on how you arrange steel reinforcement inside your concrete structure. What I show you here is called the typical non-ductile reinforcement detail. I can see this type of detail everywhere, even in seismic prone area. This is not good for the structure. We have to change from non-ductile into ductile reinforcement detail. Okay, but the practice we are doing now in Philippines, in Thailand, in Nepal, in many countries, we still continue to put the reinforcement not in the right way. So our structure cannot deform well. It will develop bad type of failure, the failure that are quite brittle. Okay, I can show you some example. This is an experiment conducted in Japan. It's a full-scale building put on a large shaking table. Okay, Japan actually invests a lot on earthquake research, so we can learn from that. So I'm freezing the video now. You don't have to be engineer. You can tell that this column cannot carry any more load. Okay, it's completely destroyed by brittle type of failure we call shear failure. So it cannot carry any more gravity load. The gravity load that transfer from the top floor down to this floor. So if this column cannot carry gravity load, then gravity load will have to go to other column. If other column also fail the same way, then there is no column to carry gravity load. Then building will collapse. Okay, so this is a normal way that how earthquake destroy the building. Earthquake will create serious damage to some critical member like columns or some important structure, and then the structure cannot anymore carry gravity load and it will collapse. This is an example. After earthquake destroy this column, then the gravity load, they will crush this column down. Okay, but this is not in Japan. This is in Yogyakarta, Indonesia. Now, after you know something about earthquake resistant design, let me give you example of real building. This is a typical commercial residential building. We have a lot of these buildings in Thailand. I think you have it in Nepal, in Singapore, in many other countries. And they actually have many features that make them vulnerable to earthquake shaking. Most of these buildings are not designed for earthquake. Okay, the first story is for business and commercial purpose. Upper story is for residential purpose. So if you take one sample of this building, you will see the structure like this. The white part show columns and beam forming a frame. And then you have the orange panel, which is the wall, actually made from brick. Okay. The brick wall actually is not the structural component, but it can strengthen the structure. It can stiffen the structure. And we normally have many partition walls, exterior and interior wall on the upper story because it's for residential purpose. But for the first story, you don't have the wall in the front, in the street, but you may have the wall on the side and on the back. So this actually makes the first story become relatively weaker and softer compared to upper story. So we have soft and weak story. And the arrangement of the wall, you don't have the wall in the front, but you have the wall on the other three sides, make it torsionally irregular. And we also do not put the reinforcement in the frame, in the columns and beams in the right way. So it is not so ductile. It's non-seismic detailing. So when it's subject to earthquake, the building will deform like this. Upper floor looks quite rigid because you have many partition wall, strengthen the building. But the formation then is concentrate only in the first story. Actually, not only in the first story, but it's concentrate in the front row of the building because we have the wall in the back, we have the wall on the side. So in the whole structure, the only critical components are the first story column in the front row. So all the deformation is concentrate in these columns. So you can expect when it's subject to earthquake, which component will fail first? It will be the first story column in the front row. Okay. Then this is what happened. I took many of these pictures in Taiwan. You can see that the front row columns collapse and it will bring down the whole building. Okay. This picture on the left lower side, what you see here is the second story, but not the first story. The first story already collapsed. The picture on the right-hand side, what you see here is also the second story. First story already collapsed. So those who were killed by this earthquake are those who slept in the first story. Earthquake happened in the nighttime. Those who survived are those who slept on the upper floor. So please do not sleep in the first floor. Okay, if you are inside this type of building. This is a second example. Another example, this is from Nepal, Sitapila area in Kathmandu. I took this when I visit the area after the Gokha earthquake. What you see here, this is a second story. The first story already collapsed. Okay. Here is another example. We have 4-story commercial residential building. Upper floor looks okay. The window is still in good condition, not much damage. But if you take a look at this particular column in the first story, you can see that the column is completely in bad shape. It's already crushed, break down. I still do not understand why it's still standing, but maybe the load is carried by other brick wall. Okay, the structure is quite vulnerable, it's quite dangerous. And you can look inside the building in the first story, it looks very severe damage by this effect. I went to many places, took many pictures. I can say that the majority of damage concentrate in the first story. So you can see the damage in many buildings initiate from the collapse of the first story. This is an interesting case when we visit this area, Chautara in Nepal. I saw this building. There's under the repair retrofitting process. They are trying to bring back the structure into the service by repairing or strengthen the building. Okay, you can see picture on the right hand side. Columns were damaged, but they put a temporary steel column to temporary support the load, and they put some reinforcement and they cast the concrete around all these older column and new column cast into one piece. So this is to strengthen the building that has been damaged by earthquake. So when I look at this, I think it's a good idea. It looks quite practical. So I bring back the drawing of typical commercial residential building in Nepal. And I give to one of my students who are coming from Nepal. And I ask him to find a way to improve this building, improve in such a way that it will be able to stand against any kind of earthquake we expect in Nepal. Okay, so he construct a mathematical model, computer model of this building. He tests and check many possible methods. Oh, I also ask him not to try the difficult way. Okay, try the way that the contractor in Nepal can handle. And I ask him not to do too much. If you do too much, then it will be expensive. So I asked him to do as minimum as possible. So he found that the best way to improve the seismic performance of this building is to do this. We call column jacketing. To cast the new column around existing column. So existing column is small and we make it larger. And he found that if we do it only for the front, the column in the back will fail. So if we do the column jacketing in the front and the back, the whole structure will be okay. So it is possible to improve the seismic capacity of existing building. And if you are going to do it in the future, you can make your new building this way. And you don't have to make a small column and then make it large later. You can just make a large column in the first story. And you don't have to make it large to the second or third story. So the change in the cost may not be so high. Your extra money required for this is not much. But you will have safer building for you to live in, to stay inside. Okay. Now, if you look at many other possible into textbook, they will give you many other ways to improve the seismic performance. Okay, the way we just discussed is this way, increase the strength of the frame. But there are many other ways, like instead of using solid brick wall, you have to change it into a softer wall, like a gypsum board or some other things. It will not create soft story effect. It will not create torsional irregularity effect. Okay? Or you can put wall in the front a little bit to prevent torsional effect. Or you will not do much, just allow the structure to deform, but make sure that the column is ductile, is more deformable. So there are many possible ways to improve seismic performance, but normally people will not do it because they do not think that their buildings are vulnerable. If they are not aware of the risk, then I don't think they will do anything. This is the test in the lab that we conduct at AIT. We just put the column into the testing frame and we wrap the base of the column by carbon fiber sheet. We call carbon fiber reinforced polymer. We are wrapping them around. And we apply the force, cyclic force on the top of the column. We also apply vertical load to the column. But by putting this carbon fiber wrapping, we are able to make this column quite ductile, quite deformable. You can see that it can deform a lot while it still can carry vertical load. Okay? So this does not look like concrete column anymore. It looks like plastic column that can deform a lot. Without wrapping, the deformation ability will be much less than this. So you can compare between the column without wrapping, carbon fiber wrapping, and the one with wrapping. So this is small modification can change the behavior of the structure. Okay. Now I want to highlight another type of building that is quite common in many countries in Asia. We call brick building. Okay, this is no concrete, no reinforcement steel, just brick. And the technical term is called unreinforced masonry building. There's a picture of one unreinforced masonry building in Nepal. You can see that it's nearly collapsed. A large number of existing buildings in Asia, in China, in India, in Indonesia, in many earthquake-prone countries are built this way. Okay, they are quite vulnerable to earthquake ground shaking. They are much more vulnerable when you compare with reinforced concrete frame building. This is show example. This is in the ancient city near Kathmandu called Bhaktapur in Nepal. Before earthquake, we have many brick buildings here in this area, but they all collapsed into this debris. You can see on the back, we have the reinforced concrete frame building standing well. Okay, so you can see the relative weakness between the brick building and normal reinforced concrete frame building. Okay, brick building collapsed in two pieces. I have many photos to show about this, but you can see the frame standing well, but the brick building around collapsed into debris. Okay, so what to do with this? If you have many weak, unreinforced masonry building, if you want to reduce the risk, the solution is straightforward. You need to replace them by stronger building. Okay. There are many possible ways to make stronger construction. One is to put reinforcement into this masonry building, or you can use a technique called confined masonry structure. But personally, I think the best way is to change them into reinforced concrete buildings, because many towns and cities, people are quite familiar with reinforced concrete construction. We just need to build more of reinforced concrete building instead of continue with masonry building. So this is another type, is a stone rubble. They are quite vulnerable as well. This shows you the wood frame building, wooden house. Okay, it's again the test in Japan. We have, let's see the video on the left. There are two buildings. On the left side, the building has been strengthened or retrofit to make it a bit stronger. And on the right, you have a typical wood frame building. Oh. Again, by the collapse, by the damage in the first story. And the one with seismic retrofit or some strengthening is still standing. So this the difference between death and this you will live or die depending on this one. Okay, then after this test for a few days, they remove the collapsed building and they apply the same level of ground shaking again. Against one earthquake. But after the first earthquake, it was damaged. The ability to stand against the next earthquake reduced. I think that is why in many earthquake events, after the first main shock, many people were afraid to go back to their home to live in their house. Actually, that is quite reasonable. Your house need to be inspected by engineer first to make sure that the buildings are still in good condition, still have ability to stand against the next earthquake. Okay, because you may have aftershock happening again, or you may have another earthquake events shaking your building. So this is an example of similar damage we found in the experiment and in the real world. We have a wooden house in Machiki town. This building was destroyed by Kumamoto earthquake. Now, I have been talking a lot about the damage to buildings and structure, but sometimes your building may continue to stand, but the earthquake shaking may have an impact a lot to the content inside the building. Okay, now you can see the computer facility, furniture thrown by the effect of floor acceleration. Okay, for some type of buildings, the content inside need to be protected as well, like hospital or some computer facilities. You need to control, reduce the impact to the content inside as well. I show you to another type of damage. This is a damage not to the building, but for transportation structure, expressway. This is in Japan. They have a column supporting this elevated expressway, and the column destroyed by the effect of ground shaking. Here is a road bridge in Philippines. So there are many possible mechanisms that will lead to the collapse of a road bridge. The piers may collapse, or the bridge girder on the top may slide from the support bearing and fall down. There are many possible ways that the road bridge can be destroyed by earthquake. Okay, and for this case, for this bridge, after the bridge collapsed, then the people built a temporary bridge. We actually need bridge because, especially after the earthquake, we need to need for many purposes. Now, if you are in some area, like if the soil is sandy type, saturated with groundwater, and subject to strong shaking, your sandy soil may turn into liquid, called liquid sand. This process is called liquefaction. And when your solid soil turns into liquid sand, then the building may overturn or may sink down. This is a picture in Philippines, and here is another one in Turkey. And this one is in Japan. Many buildings that overturn or collapse, the structure still looks okay, but the foundation already failed because the soil cannot anymore carry the load. The soil turned from solid into liquid. Okay, this is called liquefaction. When you have a soil liquefaction, it will destroy many underground structure. Okay, like For example, you may have manhole, you may have a pipe network inside the soil. If the soil is solid, they will stay at their place. But when soil turns to liquid and the manhole is lighter than the surrounding soil, it will be floated up by the buoyant force. It will create the breaking of the pipe and damage to many of the underground structure. So this shows you the manhole structure. So initially it stay underneath the ground, but the soil turned into liquid. So this manhole was floated up, punching through the asphalt layer. When you have a soil liquefaction, it will destroy many piping network inside. Okay, your water distribution network, gas distribution network, telecommunication line can be seriously affected by soil liquefaction. If you are in a mountain area, okay, earthquake shaking can induce landslide as well. So the soil mass from the mountain, from the slope may fall down into your building. Like this case is in Wenchuan in China. When you have an embankment structure, you may use this for irrigation purpose or dike. When it's subject to cyclic ground movement, it will create slope failure. When the ground moves one way, the other side of slope fail. It moves in the opposite way, the opposite side of slope fail. Okay, and after cyclic shaking, then your embankment structure will have many cracks and it may break. Like this, for example. This is a bush earthquake 2001 in India. And one single earthquake destroyed about more than 100 irrigation dam structures, small dam. Okay, it destroyed this irrigation facility in that area. And if your area is have an active fault underneath, and when you have a movement of active fault, it may break the upper soil layer as well, like this in Turkey. And this guy is standing on top of active fault, but the ground on his back moved to the right, the ground in his front moved to the left. So they are separated by several meters. Okay, this is a horizontal movement along the fault. If you build any bridge, road, or anything across this one, it will be damaged. This is another type of surface rupture by the fault movement. But this time it's in Taiwan and the fault movement is in vertical direction. So it's create kind of a vertical movement. This is actually, initially it was a flat football field and running track around football field, but by the movement of the fall, then you can see that one side is moving up by 2 meters. Actually, here is another case, a small dam, and you can see the damage to a portion of this dam. Okay, it's a Chikang Dam in Taiwan. And if you take a closer look, you can see the damaged portion of the dam. You know, before the earthquake, this part, upper part, and this part, they were in the same level. But by the earthquake, the fault movement, one side is lift up, push up, become about 9 meters higher than on the other side. It is impossible to design the dam to accommodate this level of displacement. It's impossible. Okay? So our strategy as a civil engineer, we have to try to find where are the active fault and try to avoid building the dam across active fault. But sometimes we miss that. Okay, like this one, they try, but they miss it. Now they know they have an active fault now, after it happened. This is in Kumamoto. The movement is not large, but you can see the breaking of surface soil. Okay, and the rupture continue to that building, the yellow color, and you can see the land around this building is not flat; it's deformed by the surface deformation caused by fall movement. So it caused some damage to this yellow building. And this shows the damage of fall movement or surface rupture to the road. Okay, the road was damaged by this deformation caused by the underground fall movement. So there were many impacts possible by earthquake. Another possible impact is called the fire. You may have fire disaster falling after the earthquake. Fire may be triggered from damaged buildings. Like in case of Kobe earthquake, fire broke out from 100 different spots in the city after the earthquake. And it continued like this. And because it happened at many different places, it was beyond the Kobe fire department to suppress this fire. So they just let them continue until it keeps down by itself. So this is an example of one earthquake event. You may have everything that I explained. You may have a building collapse, house collapse. You may have fire falling after the earthquake. You may have soil liquefaction in some area. And you may have the collapse of transportation structure and lifeline system in your city. Okay? It is quite, when it happens without warning, and you learn about and the disaster happens, you cannot do much. But if you are able to estimate that or predict that this might happen before it happens, if you can calculate or estimate the impact of earthquake before it happens to your city, I think you can then prepare for it. You can prepare yourself for the disaster. You can make a plan for that. Okay? So this day, it is possible to do that. What you need to do is to put a lot of information together. You need to put the information about seismic hazard, where is an active fault, where is a possible area that you can have large earthquake, what will be the maximum ground shaking it produces. This kind of information we have to first find out. Is in this layer called seismic hazard. The next layer is about geological data, because some type of soil condition can amplify the ground shaking level. Some type of the soil can turn into liquid. Okay, some type of the surface may break because of fall movement. So you need this geological data. And then you need a layer of that show where are your buildings in the cities. Buildings, lifeline, transportation system, your population. And for each element in your city, different type of building, they have different vulnerability. So we combine all this information and we can calculate the impact of earthquake, the damage caused by earthquake. Okay, I'm about to finish. I want to show you one example. This is the capital city of Bangladesh, Dhaka city. I use this to demonstrate this idea. The city has 91 wards. We can actually start from the building information inside the city. This is a building GIS database, geographical information system. And we can create a model of the entire city. we can divide the city into many sub-area. Like in this case, the city of about 7 million population, we divide into 500 or more sub-area. And for each sub-area, in each sub-area, they have many number of buildings and people in that. You can see this one is showing you the details, building density in Dhaka city. It's not uniform. They have more building in some area, less building in some other area. Okay, and we can look into each ward and we see the composition of that. How many of them, how many percentage is residential, commercial, industrial? You can see from the pie chart. And this is a population. Nighttime, daytime, we create this model based on, we collect many information of the Dhaka city. This shows you the lifeline and transportation system like road networks, natural gas distribution network. Of course, we have other detail like rail network, water distribution network, and many others. But I don't have time to show all this information. And then after we create a model of the city, we can calculate the impact. For example, this is a 500-year earthquake, one scenario. When you have the model, you can calculate the impact of many possible scenarios, maybe 100 or 1,000 scenarios. But this is just one example, one scenario. You can calculate how many buildings will be damaged, what level of damage it will be. Okay, moderate level, extensive level, complete or near collapse level or collapse level. How many of them we can calculate from that? We can also calculate the number of casualties. For example, in this case, we divided the casualty level into 4 levels. Level 1 is light injury. You don't need to go to hospital. Level 2, you need to go to hospital. Level 3 means not only to go to hospital, but need to go to ICU room. Okay, very serious injuries. Level 4 means the person is dead. Okay, so if we sum the serious level 2, 3, 4, you can create a map like this. So you will understand the need for medical emergency. The demand happened right after the earthquake. You know the location where you can expect a large number of victims. And at the same time, you can calculate the impact to medical care facility like hospital or clinics. I use a color code to show that if it's red, means your hospital, your clinic may not be in good condition. Your percent functional is less than 30. But if it's green, means that your medical facility still can be used can be used for service. So we have red, green, yellow. Yellow is somewhere in between. So you can estimate demand and you can estimate medical supply. Okay, so you can plan for medical emergency. This picture shows you the impact to school building, university, college. Some area with red color mean that area buildings will have more damage. Some area with green mean building have less damage. So you may use this public buildings for temporary shelter or for some other purpose. It's the impact to water distribution system. And it's shown by different color again. If it's green, mean low level of damage. Number of repair per kilometer is low. But if it's yellow or blue, mean very high level of damage. Okay, so we can see the impact. Which area you can expect more damage to your lifeline system. And you can design your lifeline network so that it can handle this situation. Okay, I think I'm going to skip some, but this comes to the last slide, showing that Although I show you only example for earthquake, you can do it for other type of disaster, hurricane, windstorm or flood or other type. So it can be a multi-hazard type of model. We can use this for many purposes. You can develop emergency response plan, prepare for the future disaster, emergency medical service, temporary shelters, emergency water and power, planning for critical transportation outage. You can organize emergency response exercise, or we call earthquake drills. You can check many possible plans for mitigate the risk. First, you can identify which elements are at risk, which area have more building collapse, which area have more casualties. Then you can check if you strengthen some building, like strengthen school building, how many school children you can save, how many lives of them you can save. You can check the effectiveness of this measure. You can see the impact of your building code enforcement. You can use this for future land use planning. Okay. In fact, if you are coming from insurance industry, I think you know how to use this one. You can calculate the loss. You can prepare for that. Okay, I think that's all that I want to cover. It's about 1 hour. I'm surprised that I can cover all this in a short time.
Thank you very much.
Okay, thank you.
Thank you very much, Professor Penning, for your explanations and also for your presentations of these photos and pictures, which is very interesting. And also, I think is very easy for us to follow the explanation, although many of us are not engineers, but we can see that there are a lot of factors, that we cannot control, but there also a possibility that we can also mitigate risk and also avoid the risk. At the same time, we can also having a kind of data solutions or multi-hazards mapping solution where we can also very much plan in advance. And at the same time, those who are in the insurance industry, we can see that with the mapping of those, hazard risk and also the disaster risk there, maybe we can also inching into looking at the damage that would occur, and that may be helping the society and also to the economies of the local area and also the economy of the countries. So I'm not sure whether we have any question from the floor. Is there any? Hello, professors. Could you preciously explain on how many seismic magnitudes that cause non-strengthened real wooden frame house collapse, and in which magnitude increase to make strengthened wooden frame collapse? The magnitude.
Oh, okay. I may not have that details, but the one I show you was the wooden house built in Japan, and they test this under the ground shaking. They call Kobe earthquake. Kobe earthquake happened in 1995. It actually destroyed many buildings and structures in Kobe. They use that as an example of strong ground shaking to check the vulnerability of the typical wooden house. And the one with retrofitting, they just add some component, add some wooden wall, add some frame to make it slightly stronger. I think that's all information I can explain to you.
The next question, some of the buildings were saved in the Türkiye earthquake. Some of the buildings were saved in the Türkiye earthquake. What could be the reasons? Did they consider soft story while designing?
Yeah, actually, as you see, there are many factors that can make building weak. Okay, soft story, non-ductile detailing, torsional effect. And sometimes you have all these factors without knowing. And sometimes you do not have this factor. Okay, and sometimes you make your columns larger than is required. So when you look at one type of construction, like commercial building, one building will be different from other building. And each of them will have a different property. So it's hard to tell this one. But if your building have many of these multiple factors that make it weak, it will collapse easily. And you have less number of factors that make it weak, it will have less chance to collapse. So there is a variation in structural property. It's difficult to pinpoint one or two. Okay? But in Turkey, the percentage of collapse building is very high. It means that, and one of the main reasons is the level of ground shaking was too high. And that may make engineers to come back and think again, what is the level we should aim at? Maybe 500-year earthquake is not good enough. Maybe we have to look at 2,500 year and make sure that it can handle that. I think that's the key point.
So we have to close the session for today. So now I can see that Mr. Moinuddin Ahmed from the Professional Advanced Bangladesh is here. So may I request Moin Bhai to give the word of thanks to our speaker, Professor Penning. Moin, please.
Very good afternoon to everyone. On behalf of Professional Advancement Bangladesh and Green Delta, I am Syed Moinuddin Ahmed, the additional MD of the group. Extending our heartfelt gratitude and thanks to Professor Penang for taking an extensive session on earthquake and learnings from Türkiye, and particularly sharing the findings on Dhaka city. Actually, this has been, the last few slides has been most scariest from our perspective who are residing in Dhaka. We all talk about it, what could be the devastation an earthquake to the tune of 7 or 8 Richter scale could cause, but I have seen the slides and I'm having goosebumps, frankly speaking. But nevertheless, these informations are important to plan out the evacuations and rehabilitations and how to minimize the losses. And as an insurer, I believe this kind of sessions would definitely help the underwriters, particularly when it comes to assess risk in this kind of geographical plateau. We'd like to thank AIT Extension, Professor Varawat and his team for arranging such a timely session, which needs a lot of attention from all the stakeholders, not only from the insurers, but also from city planners, the city corporations, the government ministries, LGRD, LGAD, and so on and so forth. I'm overwhelmed to see the participation that we have today, close to 150 participants at one point in time or more. We'd like to extend all the participants heartfelt thanks for attending the session. And we certainly believe that this session has helped all of us to gain some sort of understanding, as well as gaining the importance of getting to the detail of how an earthquake can actually cause the devastation. We could see our very good friend, Mr. Chanki Chetri from Nepal. Hello, sir. Good to see you here as well. So thank you so much for being here and making the event more meaningful. And as you could see, we have attendance and participants and guests from across the region. We believe these kind of sessions would definitely bring more impacts, not only to the audience, but also to the policymakers. So our support on behalf of PABL, our support will always be there to AIT or whoever would like to organize such kind of sessions, be it online, be it physical. We would love to support this kind of initiatives and look forward for having such kind of sessions. So Professor Varawat, once again, thank you. Professor Penang, thank you so much for sparing your busy time with us and sharing all the valuable information with us. Hope to be in touch with you soon. Thank you once again. Over to you, Professor.
Thank you, Moin. Thank you. Thank you very much. So there is also, I should say, it was from one of the audience, from the participants that, he's saying that, Professor Penning, from here, you are looking very smart and looking very young. So I have to say that to Professor Penning, and, the Professor Penning keeping, young always, and we're always very active, in his profession. So I would like to, again, thanks to our friends, TQR Insurance, who are sponsoring these sessions, and also along with the Nepal Insurer Associations and Professional Advanced Bangladesh. You are always friends in the insurance industry that we are working together and try to bring the topics and issues that can also transfer the knowledge to our friends and also our partner collaborators in the industry. You will be also hearing from us again, from other topics that AIT Extension and the partner offering the online sessions that relate to the insurance industries, and also the training course that organized by AIT Extensions. So please stay tuned for that. For example, we will also have the sessions, next session, online sessions that you can join and listening to the kind of a short sessions that related to the cyber risk and cybersecurity insurance, for the cyber insurance specialists. We will have a short session for this one. We also have the training course organized in Bangkok. So we will be inviting you to participate in this program and give you the QR code to look into the detail. So until we see you again in the next online sessions, thanks and goodbye to everyone. Have a very good day. Thank you.
Bye.